the factors affecting rate of reaction. Factors affecting rate of reaction. Yeah, factors affecting rate of reaction. We have plenty of the factor. We have, temperature. We have temperature as one of the factor. We have concentration. Yes, we have, of course, pressure is also there. We also have catalyst. There are times you have surface area, very important, surface area. Yeah, surface area. You see, surface area. All these are the necessary factors to talk about. Of course, I want you to understand the temperature factor can be expressed more better with Arrhenius equation. Arrhenius equation that said that, I don't want to talk much about this for now, that K, rate constant, is equal to AE minus EA all over RT. So that is it. Temperature, of course, this is just to say increase in temperature increases the rate of reaction. Simply put, increase in temperature increases the rate of reaction. Let me drop this on temperature. Let me just eliminate this side this time around. Yeah, let me eliminate this. Look at temperature factor are expressed in two ways. We have when a reaction is exothermic. Of course, exothermic reaction is a reaction that liberates heat to the surrounding environment. It's a reaction in which heat is part of the product. A plus B giving C plus D plus heat. That is an exothermic reaction. And with this, the enthalpy change is equal to negative in a reaction of this type. Of course, in every exothermic reaction, increasing the temperature, of course, does not lead the product. Increasing the temperature does not favor the side of the reaction that is exothermic. I have a lot to say here. I have a lot. And what is that? For exothermic reaction to be favored, the temperature must be what? Minimal. It must reduce temperature. That is, minimal temperature is required. Minimal temperature is required for exothermic reaction. Why? When you have A plus B plus heat giving you C plus D, this reaction is endothermic. This one is another temperature where temperature favors this. Now, I say this one must be minimal temperature. But look at this. Heat is part of the reactants. That means a reaction that absorbs heat from the surrounding environment is what? Endothermic reaction. And at this point, the enthalpy change is equal to positive. And for this reaction to be feasible, you see that it must be of maximum temperature. Yeah, maximum temperature. Temperature must be maximum. Now, but let me just say what I have to say. Wanted to say before. I want you to understand that these two processes occur simultaneously. Yes, look at this. We have A plus B giving you C plus D. This reaction are always the reversible process of each other. And if they put that change in H is equal to negative, what does it mean? It means going forward in this reaction is exothermic. Yes, exothermic. As coming backward of this reaction is endothermic. Yes, endothermic. Meaning, since the forward is exo and the backward, the reverse, endo. Now, if they said increasing temperature in this reaction favors which side? And you know the exothermic side of the reaction must go with what? Minimal or reduced temperature. And that of the what? Endothermic must go with maximum or just very high temperature. Favors, because this one absorbs heat in order for product to be formed. While the other one, the heat is being liberated. So at this point, increase in temperature favors the what? Backward reaction. Increase. Look at this. Temperature increase favors backward. While temperature decrease favors forward. So that is it. That's what you need to understand. Now, when we talk about pressure, pressure will only be effective for gaseous reactants. Yeah, pressure will be effective for gaseous reactants. And of course, let me use this equation or Haber process to exemplify that. You have the nitrogen gas reacting with hydrogen gas. They will give birth to what we call ammonia gas, the only alkaline gas. And this is also a reversible reaction. Of course, it's an exothermic type of reaction, meaning change in H is equal to negative. But let's not talk much because we are considering only the pressure effect, not the temperature this time around. Now you see here, the equation is not balanced. You are this here, you are. So let me put 3 here and of course put 2 here. So the equation is now balanced. So with this, look at this. There is 1 mole of nitrogen reacting with 3 mole of hydrogen, and both is giving birth to 2 moles of ammonia. So with this, the total mole of the reactant is 4 moles, 4 moles, while that of the product is 2 moles. Now, pressure, I want you to understand 2 moles. Look at this. Now, I want you to know that mole is 1 mole of a gas is equivalent to 1 volume of a gas, according to Avogadro hypothesis. What does it state? The equal volume of all gases at the same temperature and pressure contain same number of moles. So with that, 1 mole is equivalent to, so we can put 4 volume here and put the same thing 2 volume here. But one thing I want you to understand is that pressure is always inversely proportional to volume. So with this is the relationship. So increase in pressure must be in the direction of decreased volume. So that is what I want you to get. Why decrease in volume must be in the direction of, or increase in volume must be in the direction of decreased pressure. So increase in pressure, look at this, increase in pressure favors the sides with less number of molecules. That is the ammonia side. So increasing pressure will lead to more formation of ammonia. Why decreasing pressure, of course, and vice versa to decrease in pressure. So this is just what you need to understand. Catalyst. You can see catalyst is not that thing than a substance that alters the rate of chemical reaction. Catalyst is a substance that alters the rate of chemical reaction without itself being affected. Yes, that is it. And how does catalyst alter the rate of chemical reaction? By creating a lower energy pathway whereby reaction can easily take place. So that is the work of catalyst. We have different types of catalysts. We have catalysts that actually promote, we call them proton. And we have the one that will delay the progress of the reaction, we call them inhibitors. So but I want you to understand that catalysts alter the rate of chemical reaction by reducing the what energy barrier of the reaction. That energy barrier is what we call activation energy. In case they ask what is activation energy, it is the energy barrier that needed to be broken before a chemical reaction takes place. Surface area, that's three before we conclude this session. Surface area. Please, I just have surface area. One thing to say here, surface area is mostly for solid reactants. Mostly when we talk about, example, kakotere, this is a solid, we call it limestone. Now, this can be of 2 forms. We have the rump form, and we have the powdered form, rump form, and the powdered form. Yeah, cathode 3. So that is a calcium carbonate or calcium thiazocarbonate 4. In that cathode 3, there's something I want you to get. Yeah, cathode 3. Then, the geologists, when they go to field to know whether if a rock is carbonate, how do they know? A carbonate rock is a rock that traps the CO2 gas. They go with a chemical called HCl. Yes, HCl. And what do they need to do? Just to pour it on the rock surface. If a noise, if it make a noise like that, that is, it means the gas have emit off the surface. So that is it, emit off the surface. The gas don't escape. Now, but you see, at times the rate of effervescence shows the rate of reaction. Increase in effervescence shows increase in reaction rate. Now, what do I mean by that? See, if the rock is in powdered in lump form, the surface area, that is the volume ratio for the reaction to take place, will be very minimal. But when you grind it to a powdered form, you see the effervescence will increase owing to the fact that there is more surface area for reaction to come into play, or there is more volume ratio for reaction to take place. So that is why making it to be of powdered form means increasing the surface area, which lead to increase in reaction rate. So don't forget that. I don't want to talk much. That's why whether you are putting all this calculus theory plus HCl, HCl, yes, HCl, or you are just doing, in fact, let me not put this, let me just put calculus theory. When you hit this, you have something like calcium oxide solid, C plus CO2 gas. Let me put it this way now. This is solid. Now, what I want to do is that the rate of reaction here is already being measured with respect to the formation of CO2. And that is why if this is an equilibrium reaction and they ask you what is the equilibrium constant, Kc is only the concentration of CO2 because that is gas. So CO2. Kc is only expressed for aqueous solution and gas. So these are matters that we need to know when we talk about factors affecting rate of reaction.